All right, welcome back. We are in the new machine learning techniques track, starting with a talk by Alex Ingerman, who's product manager at Google. Alex, you were also speaker at PAPIs in Valencia 2 years ago, but back then you were at Amazon. Right?
Yeah. So it happens.
Congratulations on the upgrade. No, I'm kidding.
No comment.
No, I think it's great to hear about decentralized machine learning, especially from Google. So yeah, very much looking forward to your talk. And please, everyone, let's welcome Alex on stage again.
All right. Well, thank you everybody for being here. It's day 2 of the conference, and it's afternoon, and it's right after lunch. So these are like formidable barriers. I appreciate everybody who's made it in. So I want to talk to you about machine learning and decentralization. And it's really broad. Like, what does decentralized mean? Well, there's been a lot recently in the news and in the sort of industry medium about things like blockchains and smart contracts and cryptocurrencies. All of these things are based on decentralized approaches. And these are really exciting. I regret to inform you I'm not going to talk about any of that. I actually didn't think I would hear anything about blockchains throughout, but somebody, I think the gentleman from Seed AI, did mention them yesterday. So there was a mention. What I want to talk to you about instead is smart devices and edge devices, and the ways in which we might consider extending our machine learning capabilities towards these smart devices. And really crucially, what does it mean to run machine learning on devices which may be installed in privacy-sensitive environments, for example, in public spaces or perhaps even in our homes. And this talk has just 3 simple purposes in life. I want to talk about on-device machine learning, and I want to convince you that it's important and it's different. It's not just the same machine learning where you know how to do, just running on a slightly different hardware. I want to talk about some specific approaches towards decentralized machine learning. And I want to make you really excited, uncomfortably excited, about a technique called federated learning, which is a new and exciting field about applying distributed machine learning techniques to a very heterogeneous fleet of devices out there. So what's a device? Let's just start with that. A device is a lot of things. Perhaps the most intuitive thought you may have is a phone is a kind of device. And phones are definitely the most capable devices out there. There are a lot of them, and they're really personal. There are a few things that are as personal of a device as a phone. So a question to the audience, and I promise it's the first and last bit of audience participation. Raise your hand if you remember the last time you were away from your phone for more than, say, a couple hours. Less than half of the room? In a survey from 2015, a quarter of people surveyed said they couldn't remember at all the last time they were away from their device. And something like 79% of people said, well, I'm away from my device for less than 2 hours a day. So these phones are everywhere. They go with us wherever they go. They're just studded with all of these sensors on them. They have location, they have sound, they have ambient light, they have a camera. All of these sensors are there, and through the magic of commercialization of technologies, these sensors are getting better and better, and the phones are getting cheaper and cheaper. And of course, we don't just carry these sensors around. We interact with these phones. We use them to look up information, we use them to communicate, we use them to take photographs. These phones are just incredibly personal. And the way they interact with the physical world and the way we interact with them is this absolute wealth of information. And we should be considerate about how we might use that information and careful as well. Then there's a different kind of device out there, and I call them connected things. Internet of Things is another common name. There are quite a few of them out there, and oftentimes they're all around us without us necessarily knowing they're there, whether it's a security camera, whether it's some kind of an of a traffic sensor, whether it's any kind of ambient environment device that are all around us. There's an estimate that in 2016, so that's already 2 years ago, there were 4 billion consumer devices out there, in addition to many more industrial devices. And these devices are also getting more and more capable. There's often no longer just a single-purpose device that can only do one thing. Now they have many sensors on them, so they can do a lot. And they're gaining their internal compute capabilities as well. And then the last category, robots are kind of this unclear category into which you can lump anything from a vacuum cleaner that knows how to navigate around your home all the way out to a self-driving car. You might call anything that has some autonomous capability to navigate the physical world as a robot. And again, we have quite a few of them out there. We'll have many more. And these devices are also quite capable. So devices, I hope I've persuaded you that we should at least think about how we might use them. Then there is this natural question of what's so different about machine learning on device? Why not just take what we already know, how to do machine learning, and just do the same thing, but on device? This picture here is how most machine learning everywhere is done today in the world. You essentially have this idea of a centralized smart server, and application developers build applications that run on these servers. Users interact with these applications. The interactions generate log data. We can mine the log data for insights, build machine learning models, deploy a better version of the feature. Users go use the feature, generate more data, and you have this virtuous cycle. The more an application gets used, the better the machine learning model that's built on the log data, the smarter the application. And this works really well. I mean, this is the dominant industry pattern. But it's kind of this interesting observation that all the smarts in this picture are in the server land. The device is kind of dumb in this picture. Its only purpose in life is to issue a request, get a response, and presumably some kind of a smart response, and then maybe render some UI on top of it and present that UI to the user. And if you just observe that a device is just a very different category of user agent, it's no longer a web browser from 10 years ago, which is what much of this picture really looks like. These devices are more personal, they're more numerous, they're more capable, they're more autonomous. They can do a lot more if only we had a good mechanism to use them. So on-device machine learning, the very first step towards on-device machine learning, and this is becoming quite common, is to take prediction generation and move it out to the device. So instead of having this little brain in the cloud and you make requests into the server to make a prediction, you get prediction, you do something with it, why not take that model and move it out to the device itself? Many devices out there are perfectly capable of running machine learning models and generating predictions. And once they do that, there are tons of benefits to it. You get often you will get a much lower latency because you no longer have to make a network request to get a prediction. In general, this approach is very network friendly. If you have data caps, these data caps no longer apply if you don't have to make a request out there. In fact, your application can work offline entirely. On-device prediction generation is great for privacy because you don't have to take a piece of data, potentially sensitive piece of data, and send it off the device somewhere else to make a prediction, and then either you have to promise that you won't store that piece of data, or you have to be very careful about guarding that piece of data if you do store it. You get access to all the sensors on the device much more naturally than if you had to take the data from the sensor and again ship it off to some server to process. And the power utilization, which is not to be underestimated in battery-powered devices like, say, a phone, is incredibly more efficient to do prediction on device than to spin up a radio stack, make a request, receive a response, maybe power down the radio stack if you're careful. This could be a difference of a couple of orders of magnitude in battery usage per prediction. So lots of really good stuff here. But there is this question, okay, so we've moved the prediction out to the device. How do we continue making that model better? And there is kind of a natural answer to that, which is anytime we made a prediction on device and we vended that prediction to a user, we have an opportunity to actually generate a new training example because we can predict what the user will do, we can observe what the user has actually done, and record all the context around it. So now we have an example with lots of features, and we have a label. So we can get the training data, and then what do? The most natural thing is to take the training data and send it back to the server where you can aggregate it and build the next version of the machine learning model. And then you can take that model and redistribute it back to the devices. So that closes the loop nicely. It looks a lot like the picture we've seen earlier with machine learning in the server land. But now we have to ask all these questions. What about sensitive device data handling? Just said that on-device predictions are really great for privacy because you don't have to send the data off the device somewhere else. Well, if you take that learning data you generated at the end and send it back to the server, that's not so good for privacy anymore. What about the connectivity constraints? If you have predictions generated in a context where you don't have a lot of connectivity, maybe you're working entirely offline, then your ability to send the training data you've captured back to the server is also similarly constrained. And then there's the question of personalization, and that's a really interesting one. Personalization is a very desirable thing out there. It's a very desirable feature to add to a wide variety of products. And personalization is actually really hard. It's really hard in the context of a global model where you have one model which is the same for everybody or for every device. But you're attempting to get that model to give you personalized results, usually through the mechanism of really clever feature engineering. So you're trying to build out features that can take context of how the model is being used and give back personalized predictions. It definitely works. That's pretty much the only way personalization is done today. But it's not easy. It's much easier to make a global model that works the same for everyone than to make a global model that can return personalized results. So the next step on this journey towards taking machine learning on device is to move the learning process onto device itself, which is actually just shorthand for personalization. That is the most natural way to apply it. The idea is conceptually very simple. Once we've generated training data on device with a label, instead of centralizing the training data and then running a machine learning algorithm on a centralized location, why not keep the data exactly where it is and take the machine learning algorithm and move it to where the data is? Think of it as having many independent models that are each evolving independently. The many devices out there are perfectly capable of running this kind of software. There are many machine learning frameworks, TensorFlow being one of them, that is very happy to run in a wide variety of devices. So this actually works pretty well. And it's an interesting approach for personalization because it presents kind of a radically different way to do it. Instead of trying to be really clever about engineering the features for one global model that will give personalized results, you can start with one global model, and then you can improve the model on each device with data that is tailored or only generated on that device. And so now you have a model that's kind of implicitly personalized in the example space instead of a feature space. You also, of course, have a situation where if you have 1 million devices, now you have 1 million models instead of having one global model. So personalization, this kind of personalization is really powerful, but there are also these questions. What about? What about the new user experience? If everybody starts with the same global model and then personalize it, then a new user who shows up gains no benefit at all from the learning done by the other users of the application. They have to start anew. And the rate at which they generate new examples could be quite low. It could take a long time before this model really starts adjusting to that user and becoming personalized for them. And the flip side is for devices that do exist kind of side by side with each other, there is no mechanism for them to benefit from one another. So we all know that models start becoming out of date the second they're created, the world changes. And each device basically has to adjust to the changing world on its own. There is no ability there to benefit from the peers' data to jointly adjust. But you do have all these other benefits, including completely local learning. And since no data leaves the device here, you have these great privacy guarantees. The data just stays on device, period. So the third step, and this is the step that I'm really excited about, and I hope you'll be excited about as well, is take the machine learning and run it across devices. This is the approach known as federated learning. It's quite an active area of research by Google and other collaborators, both academically and at other companies. And I'll talk a little more about how Google uses that in a little bit. But first, the basic idea. Starting with the same setup as we had for personalization, which is we have some kind of a baseline model on the server, and we have mobile devices, and each device has its own local training data. We can send that baseline model out to each device, and then we can train an improvement on each device, just as we did in our previous example. But then, why not take the improvements, only the improvements, think of them as the deltas of the weights in the model, and send them back to a server where they can be averaged together to yield a new model that is actually a combination of the training results on individual devices. And that happens without sending any of the data to the server. So the data never gets centralized, but the updates get aggregated, and then we have a new improved model which we can send back to the devices. And that's not all, because once the model, this improved global model makes it to the device, you can go right back to the local training examples you already captured and update that model with these training examples. So you get a better global model, and then you also get the personalized on device. You don't have to choose, do I want a better global model or do I want personalized models? You can have both. You might say, well, isn't it just like distributed optimization? What's the difference here? And the difference is all in details. The realities of running federated learning out there in the world is that we run an environment that looks nothing like a data center. We have a very large number of devices. Instead of having, say, 100 worker nodes in a distributed TensorFlow job in a data center, you might have 10 million devices out there that all have some data, maybe 100 million, maybe 1 billion. These devices have very limited communication. You only get a few rounds at a time, especially if you're trying to be respectful of the device system health and not do things like fire off a bandwidth-intensive operation while the user is watching a movie or doing something to interfere with their experience in any way. You have highly unbalanced data. Some devices will have lots of data, some will have little, some will have none at all. There is no guarantee whatsoever that the data is distributed on these devices in any kind of a way that you can make an assumption on. The only assumption you can make is that there are no assumptions. And the devices are unreliable. They're unreliable in the sense that you cannot rely on them being available and behaving nicely for you to run your distributed optimizations the way you would run in a data center with parameter server. Devices go online and offline. People get on airplanes. People drive through tunnels. People do things with their phones that make them slow, and the operating system may start killing processes. Who knows? And then, of course, there is dynamic data availability, which is, if you have devices distributed around the world, and you also have a rules that only devices that are, for example, plugged in and on unmetered connections are participating, well, it's only midnight in some parts of the world. You only get these devices online. You don't get devices at the same moment from the parts of the world where it's mid-afternoon. So federated learning is different from distributed optimization, but it turns out entirely feasible. Again, this has been a very active area of research. Many papers have been published about federated learning. I encourage you to check them out. I'll have a couple of references, I think, at the end here. It turns out that a lot of these approaches, a lot of these problems can be controlled by having a central server that is smart about which update it receives. So instead of trying to coordinate updates from every client that's ready to give you an update, it very deliberately selects which clients it wants updates on for any given round of model training to control for all these different sources of bias and steering in the wrong directions. So let's talk about privacy for a second. We've had this picture earlier on that each device learned an update, which is just to say, let's call it just weight deltas, and we can send these weight deltas to the server where they can be aggregated together. It's really reasonable to ask, is that really private? Is there any information in these updates that might be sensitive? And the answer is, it depends. For some models, it may not be sensitive at all. For some models, an update by itself can be very revealing about the model usage on a device. I'll give you a simple example. If you have a model that is a keyboard model where you try to learn and predict what is the next word the user is going to type, a model update can be essentially interpreted as a bag of words of everything the user has typed. Incredibly privacy sensitive. And so the question is, could we do better? Is there some way to secure these updates? Before we get there, let's observe some ways in which doing this kind of operation in a federated setting is already better than collecting all the data in a centralized location. One, the updates are ephemeral. You don't need to store these updates. You only need to receive them and process them and throw them away. There is no requirement to store them. That's pretty good. Two, the updates are focused in the sense that a training data example may have all kinds of information. But what makes it to the server has already been through the machine learning process and has been distilled into weight updates. So if there is some sensitive data in the examples that is not used by this particular model, there is no trace of it in the weights. You only get to use the data that is needed for the machine learning model itself. And then, we don't need these updates individually. We only need to compute an aggregate of these updates. That is all that's needed to create a better global model on the server. So wouldn't it be really great if all of these clients can submit updates, and these updates could not be read by the server individually, but could still be aggregated into something that is a global model that can be read? It turns out that there is a very well-established body of literature and an area of computer science that usually goes by the name secure multi-party computation that enables us to do just that. It enables each client to encrypt its update with a key that the server does not have, but in a manner that allows the server to take these updates and run mathematical operations on them, in our case an average, without having to decrypt them. You can average all these updates in their encrypted form. And once you've averaged enough of them, where enough is a configurable parameter, you can reconstruct a decryption key that is only good for decrypting the aggregate. It's absolutely useless for decrypting as an individual update. These updates are completely unreadable by server at any point. And again, they don't even have to be stored. You throw them away as soon as you receive them. So we call that secure aggregation. We have a paper about it out there. It's I would call it a really complex implementation of a really simple and powerful idea from secure multi-party computation. So this is the federated machine learning world, a world where you can run distributed optimization across devices without having to take any data off the devices, and with ability to protect even the updates that leave these devices to be only useful for the task of creating a better model through weight averaging and nothing else. So what are some good applications of that? In some sense, it's any application where you have data that is natively generated on devices. Anytime you have data on devices that is more relevant than the data you have on the server, consider whether it makes more sense to take all that data and ship it to the server and potentially deal with the expense and the difficulty of protecting that data if that data is sensitive or very large, or bring the machine learning process itself to the devices. So privacy is a significant reason why you might consider running the machine learning process on the device itself. Data size is another example where it may just not be feasible to send that data to the server. There is currently this restriction that this is an approach fundamentally for supervised machine learning. And furthermore, you have to be able to get labels on device. And sometimes you can get labels on device explicitly from the user. Oftentimes you can get them implicitly by predicting what the user would do and observing what the user will actually do. Some motivating examples I'll run through really quickly. One is language modeling for mobile keyboards. We've done that at Google for Google Keyboard, and we've published a blog post about it on Google Research blog. Given a keyboard, it's a place where you can really help a user be more productive on a mobile device by giving them a smarter keyboard that lets you accomplish things quicker. But of course, it's a very privacy-sensitive place to play in. And so we've done models in Google keyboards that run on many, many devices out there today in the real world to help users get things done without taking the data off the device. Voice recognition is a similar category. Anytime you have really hypersensitive personal data, medical data is an example, and there's been some really great talks in the last couple of days about applications of medical data. If you have a device that has medical data on it, federated learning is a fantastic approach to making something with that data without going through this whole process of trying to get all that data into one place and then protecting it and incurring this enormous liability of having this personal data. And then anytime you have a model that wants to incorporate physical context, anything a device sensor can do for you, or device virtual state, for example, what apps are running on a device right now, these are all sensitive things, so it makes a lot more sense to use them on the device instead of shipping them off the device. I think I'm probably running over time, so really quick recap. Devices are powerful, devices are personal, and devices are here. You know, this is not some science fiction thing. In 10 years' time, we'll have so many devices around us. All of these devices are around us or with us right now. And to make the most of these devices, instead of treating them as just conduits to send in the data to a centralized location where you can run machine learning, we can instead look at a world where we bring the machine learning onto the devices themselves and use the data on devices and use techniques like federated learning to make many devices collaborate with each other without sharing their data with each other or with a central server. And the place where you might consider federated learning are when on-device data is too sensitive, when it's impractical to upload, or when you really want large-scale personalization. All right. Thank you very much for sticking with me through this talk.
Thank you. Any questions for Alex?
Hello, it was a really interesting presentation. I've got a simple question. I was wondering how you do the validation of the federated algorithm without data.
Sorry, I didn't catch the end of it. I can't quite hear.
How do you do the validation of the federated algorithm without the data?
The federated learning process by itself, you know, there is a word learning in it that is a little bit misleading almost. It's really federated workflows. The key thing is to bring any kind of machine learning workflow directly onto the device. So to evaluate whether a model you've learned in a federated setting is any good, you actually bring your evaluation onto the devices as well. You have each device, for example, when it creates its training data, start automatically splitting off its training data into training and evaluation set. You run one workflow to build the models on the training data. You run a different workflow to compute an evaluation metric on the evaluation data, and then combine that evaluation data on the server the same way you would combine the model updates to yield an aggregate update. So it's really taking any part of machine learning workflow and making it run in a federated setting.
Thank you. Another question is, isn't this system of federated learning vulnerable to some kind of attack from the device where the device sends wrong data in order to corrupt the central model? Mm-hmm. And how can we protect against that?
It's a really good question. It's one of the areas of research in federated space is dealing with different kinds of attackers. And there are many kinds of attackers. Anything from attackers who want to influence a model to be in their own direction of some kind, to just kind of trolls who would like to see the world burn, to who knows. Couple answers. One is, this actually is not very different from an approach you might see where you have mobile applications that just takes its training data and sends it off to the server. The attack vector is similar in that attackers can send you bad data. So there are the approaches that you might take for verifying the data. On server side, you might take the same approach and run it on device to try to weed out bad data examples or bad attackers. In the On top of that, in this federated learning world, the server has a lot of the sort of practicalities of making it work are all about server logic, about what will the server accept or not accept. And the server cannot look inside an update, but it can certainly do things like try to determine whether a client is legitimate or not, or it might rate throttle the number of updates any client can give to it without looking inside the update. So these are the kinds of approaches you might look at, but it is, honestly, it's an active area of research.
Thank you. So you talked about all the advantages of federated learning, and that's really exciting. What are the current roadblocks that you see that have to be overcome? And also, are there any performance penalties? Like, what are the problems with it today?
The main roadblock is this is a new technology. And on the surface, I might hand wave and say, well, it's just like standard machine learning. It just runs in a federated space, but it looks exactly the same. And oftentimes it does, but essentially we have not yet, we at Google have not, and we don't think anybody else has, yet built up this experience of running it across a great number of all kinds of different use cases. We have focused on specific kinds of use cases, and we've run into occasional roadblocks, mostly around the software engineering side, not the approach side, but there are some things which we still don't know how to handle well. The most obvious one is any kind of model that deals with, that makes assumptions about batch sizes is going to have a little bit of a hard time with an approach like federated learning, which sort of imposes its own batching on top of it. And there are some ways to deal with that, and oftentimes it's not the end of the world if you have to change your batching strategy around a little bit, but that's one example. So I guess to make a short answer is it's still a new thing, so a major roadblock is it hasn't been proven across a large number of use cases yet. As far as speed, it's kind of a mixed bag. It's certainly like if you compare a, in a lab environment, a data center versus a fleet of unreliable devices that can be online, offline at any time, in that world, the data center will win. There's no question about it on speed. In the real world, it turns out that the latency of building all these data pipelines to bring the data into the data center and reprocess them and run them into a machine learning process is actually often, just through implementation, is on the order of days, weeks, sometimes months, depending on how fast your pipeline is. And sometimes this kind of on-device approach is faster by default because it's by default an ongoing process. It never stops. We've certainly seen environments where we've trained high-quality models in a matter of days, where before they took months, not because they needed months of compute time. It's just like that's the ways the pipelines were built. And you replace that pipeline with a pipeline that moves faster, and the results come in faster.
Let's maybe take one more question, but let's get Jim set up in the meantime, so that we save time. Who was first? Oh, you asked too many questions over the conference.
How would this relate to something where your model might have like localized variations? So I'm thinking of like epidemiology, for example, where you might have a centralized model, but then actually there needs to be sort of localized differences as well based on sort of localized requirements or whatever. But with the, because that wouldn't necessarily be localized to one device per se, but it might be like a geographical thing. Does that sort of affect how this would deal with those sorts of situations? Because I could see it being very useful for that because of like the health-related security issues and other things like that. But.
Let me see if I give it a shot, but I'll definitely be around as well. Like if I'm not getting the question quite right. You don't have to learn a model across the entire population you have that's exactly the same. Given the availability of federated learning on devices, you can break up your devices into independent populations and be learning models within each population that are a little different. So that allows you to have models that are, for example, only for people in a particular geographic location, or only for people with a particular marker or flag to their application.